Welcome to This Explainer. Okay, today we're unpacking a fascinating and, honestly, kind of surprising mystery right at the bleeding edge of artificial intelligence. We're living in an era where vision language models can literally write code, pass the bar exam, and analyze incredibly complex medical charts. Yet, researchers from UNC Chapel Hill have just uncovered this bizarre blind spot. It turns out, some of the most highly advanced, multi-billion-dollar AI models out there completely stumble on spatial tasks that a human toddler can do without breaking a sweat. It fundamentally challenges how we think these models actually see the world. So let's just dive right into this. Take a look at this visual puzzle on screen, and I actually want to challenge you directly to solve it right now. You see an image of coffee cups arranged on a wooden table, right? But there's a large black rectangle deliberately covering the top right section. The instruction is super simple. Count the exact total number of cups in the image, assuming that the pattern continues behind that black box. Go ahead, take a second. You got your number? Well, if you're like almost every human tested, your brain instantly recognized a grid. You saw 4 columns and 4 rows, multiplied them in a split second, and immediately knew the answer was 16 cups. You basically imagined the missing cups. But here's where it gets wild. When researchers fed this exact same image to GPT-4o, one of the most powerful AI models on Earth, it completely hallucinated the math. It looked at the image and reasoned something like, okay, there are 3 rows of cups visible and 5 cups per row. There are 2 additional columns hidden, which means 7 cups per row, so 3 times 7 equals 21 cups. It guessed 21. It fundamentally failed to grasp the overall physical structure of the whole grid. Now, what you just effortlessly performed is a cognitive function called amodal spatial reasoning. Basically, it's the ability to infer and understand the invisible parts of partially hidden objects or scenes. As humans, we develop this really early on. We know that when a car drives behind a tree, it doesn't just cease to exist, right? Our brains take past experiences, context, and visual patterns to construct this cohesive world model. We mentally fill in the blanks. But the big question we're asking today is, do modern artificial intelligence systems possess this same internal world model? Historically, actually evaluating this in modern vision language models, or VLMs, has been incredibly tricky. See, older vision-only models could be tested by asking them to literally redraw or inpaint missing pixels. But VLMs like GPT-4o or Claude, they don't output pixels, they spit out text tokens. So if you show an AI a random messy pile of coins with a chunk covered up and ask it to describe what's behind the cover, there's literally no objective way to grade its text answer. Why? Because even a human couldn't perfectly guess how many random coins are hidden in a pile. Which brings us to Section 1, the capture benchmark, measuring what AI cannot see. To actually solve this testing problem, researchers created a brand new, highly controlled evaluation method designed specifically to test this AI blind spot objectively. They called it the capture benchmark. And here is the brilliant simplicity of how capture works. First, you show the AI an image where objects are arranged in a regular, predictable pattern, like a grid of cups or maybe a circle of dots. Second, you deliberately occlude or hide some of those objects with a solid black box. And finally, you ask the AI to count the total number of objects in the entire scene. By asking for a final count, the researchers gave themselves an objective, mathematically verifiable way to test if the VLM actually understands the hidden pattern. If it understands the physical space, it gets the math right. If it doesn't, well, the count is just wrong. And this really brilliantly illustrates the depth of the test. The researchers didn't just stop at one type of image. They actually built 2 entirely separate datasets. On the left, we have Capture Real. This uses natural, messy, real-world photos, stuff like bottle caps, bread rolls on a baking sheet, or almonds. Then on the right is Capture Synthetic. These are perfectly clean, computer-generated shapes, like blue squares or red dots. This dual approach is super smart because it ensures that if an AI fails, we know for sure it's not just getting tripped up by a messy background texture. We're isolating its pure spatial reasoning skills. All right, moving to Section 2. Humans versus artificial intelligence, the results of the capture test. So what actually happens when we pit average humans against the most sophisticated models on the planet? Well, the researchers measured performance using a metric called SMAP, which for our purposes, we can just think of as a simple error rate. Look at these numbers. On real-world occluded images, average humans achieved a tiny 3.79% error rate. And on the clean synthetic images, human error was practically zero, sitting at 0.92%. Now look at the AI. GPT-4o, the absolute best performing model of the bunch, had an error rate of almost 15% on real images. Intern VL2 set at an alarming almost 33% error rate. So yeah, the AI models are failing spectacularly at a task humans just breeze right through. Now, what's really fascinating here is how the error rate correlates with the size of the black box. For us humans, our performance remains rock solid even when you hide more and more of the objects, because we immediately grasp the overall pattern. Making the box bigger doesn't break our mental model. But for the AI models, their performance directly plummets as occlusion increases. The more objects you hide, the higher the AI's error rate climbs. They aren't inferring a pattern at all. They're literally just guessing in the dark. Oh, and get this. Here is a particularly wild data point for you. The researchers tested a model called Momo. Now, Momo is unique because it was specifically trained on millions of examples to explicitly point and count directly at 2D coordinates in images. You would absolutely think it would dominate this test, right? No way. Momo still suffered a massive 32.49% error rate on real occluded images. Even an AI specifically built to count visual objects utterly collapses the second a piece of black paper is thrown over the scene. Which brings us to Section 3. Why does AI fail? Let's break down the breakdown. So we're at a critical junction in this explainer. Why is this happening? Is the AI simply bad at the act of counting, or is it fundamentally incapable of digital imagination? To figure this out, we need to break down the actual steps required to solve a capture puzzle. To get the right answer, a brain, whether it's biological or artificial, must successfully execute 3 mandatory steps. Step 1, recognize the visual pattern from the visible parts. Step 2, handle the occlusion, which means projecting or imagining that pattern into the hidden space. And Step 3, accurately count the final total. So the absolute crucial point here is pinpointing exactly where the AI's brain short circuits. Is it failing at Step 2, Step 3, or both? To isolate the exact point of failure, the researchers designed this truly ingenious test they called the Oracle experiment. They thought, okay, what if we just remove the visual burden of finding the objects altogether? What if we literally feed the AI the exact X and Y text coordinates of every single unoccluded visible object right there in the prompt? This acts as an oracle, whispering the precise visual layout directly into the language side of the VLM. The logic is, if the AI still fails to guess the hidden pattern after we give it the layout, we know for sure it's a profound failure of spatial reasoning. And the results of this Oracle test were incredibly revealing. Check this out. Under normal occlusion, the average AI error rate was 25.6%. When the researchers gave the AI the text coordinates of just the visible objects, the error rate dropped, sure, down to 17.3%. But then, when they gave the AI the coordinates of all the objects, effectively completely solving the visual aspect for it on a silver platter, the error rate still sat at 10%. This proves 2 huge things. First, VLMs really do struggle to just count basic objects in an image. But second, and honestly way more importantly, even when you give them the perfect visible layout, they still totally fail to imagine the missing pieces. This leads us right to this definitive conclusion from the researchers themselves, and I think they hit the nail on the head here. VLMs are partly limited by their inability to imagine the missing visual information. Unlike humans who immediately form a rich 3D mental architecture of the space we're looking at, these models are largely operating on surface-level visual features. They see the pixels, they can identify a cup, sure, but they absolutely do not possess a true spatial world model running in the background. So let's talk about Section 4, the real-world stakes, out of the lab and into the world. Let's move to the big picture and see how this builds into the real world. Because while counting computer-generated blue squares behind a black box might seem like just a fun little academic parlor trick, the implications of this spatial deficit are actually incredibly serious for the future of tech. We are actively deploying these vision language models into highly complex physical spaces right now. Think about autonomous driving in a busy city. A pedestrian steps halfway behind a parked van. Does the AI's internal model still track that pedestrian's hidden body? Or think about operating robotics in a cluttered warehouse where boxes block other boxes, or inspecting components on a dense production line. In the real world, occlusion isn't the exception, it's the rule. Almost nothing in a man-made environment is perfectly visible at all times. If an AI is going to interact with our physical world safely, it absolutely must understand that a partially hidden object doesn't just vanish into thin air. Which leaves us with this final, really vital question to ponder today. If artificial intelligence still struggles with the basic object permanence that a human infant grasps instinctively, can we truly trust it to independently navigate and make decisions in our complex physical world. The capture benchmark shows us that while AI has conquered language and logic in so many ways, it still has a very, very long way to go before it can truly see the way we do. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and we'll unpack another fascinating topic next time.